My name is Siheng, and I'm from Columbia University, Department of Biomedical Engineering.
And I'm Amy, and I'm also from Columbia University, the Department of Bioengineering. We work with Henry Huss, who does mostly research on kinesin motors and microtubules. And what we usually do is we attach these kinesin motors with their heads up, so that the double heads are actually moving the microtubules around. And we use the system to assemble things like long wires and spools. And in order to assemble these things, we usually use biotinylated microtubules. And we have a streptavidin molecule in solution. Since streptavidin has 4 binding sites, it can actually bind to multiple biotins. So if you imagine 2 microtubules heading towards each other, and one biotin site is filled with a streptavidin molecule, and it runs into another microtubule with another biotin site that's free, then they can actually stick together and start forming structures. So that's what our lab generally does. So what we've noticed in our experiments is that streptavidin binding onto biotinylated microtubules is a negatively cooperative process, meaning that as more streptavidin comes in, then it's harder and harder for excess streptavidin to keep binding to the microtubule. And a normal Langmuirian curve doesn't really explain this. So what we wanted to do is we wanted to find a model that fit our data and also provided some explanation as to why the data is as it is.
Since most of the protein process have a small dissociation rate, so generally the process will not reach equilibrium in the very short time. So we develop a kinetic model for our streptavidin loading experiment, and the kinetic model depends on 2 factors. The first is the probability that the streptavidin molecule will hit the surface, and the second term is the sticking probability, and we extend this kinetic model by putting activation energy into the sticking probability, and we extend activation energy into depends on the coverage theta and the intrinsic rate of binding. And we use the kinetic equations to fit to our data set. So from the figure, we can see that our model fits reasonably well compared to the Langmuir type process. And the second probability of streptavidin binding is a multivalent binding process. So the process was decomposed into 2 steps. The streptavidin first bind to one biotin, and then it will bind to the neighboring site biotin. And the kinetic rate is dependent on the probability that the neighboring site is not occupied. And we solve these chemical equations, and we gave this figure. And if we look at the figure, we can see the process is divided into 2 phases. The first phase is dominated by the double binding species, and the second phase is dominated by the single binding species. And the turning point occurs when the streptavidin concentration is the half of that of the biotin concentration. So that may imply the competition between single binding and double binding process. From the fit, we see that it doesn't fit as well as the kinetic model, so it may not be a good explanation for our process. And we also make our supporting calculations to support our theoretic calculation, and Amy will introduce that.
So we actually wanted to check whether or not the parameters that we get out of our fit make any sense at all. So from the kinetic model, which fit much better than the multivalent binding one, we can actually take one of these terms, and this actually indicates the energy, the interaction energy between two streptavidin molecules on neighboring sites. So what we did was we considered two different interactions between the streptavidin molecules. One is the steric hindrance of one streptavidin molecule occupying a space. The biotin is actually free to move around, so the streptavidin molecule floats around in space, and if another streptavidin molecule wants to adsorb, depending on if one of them is already bound, then the other one has a probability of not actually making it to the binding site because of steric hindrance. And so there's an entropic cost to having a streptavidin molecule bound to a site. The other interaction that we considered is an electrostatic interaction. Since these are the same proteins, we assume that they have the same charge, and as like charges opposite of attract. Repel each other, yeah. Since like charges repel each other, then there would also be an extra energy cost to adding an extra streptavidin in close by. So based on these two calculations, we actually conclude that the hindrance energy is around 1 to 2 kT. And what we find from our fit is that we would expect an interaction energy of a little bit higher, like around 4 kT. And this could be due to just some calculation errors or some rounding approximations that we had to use in order to make these calculations easier. But they're within order of magnitude, and they seem to fit reasonably well. Additionally, we also predicted an activation energy barrier of just one streptavidin molecule adsorbing, so the intrinsic binding energy. And that agrees with values that we find in literature. So in conclusion, the big picture is that if you want to assemble something, or if you want to model self-assembly of things that are densely packed, or if they have a possibility of interaction, it's really important to consider what exact model you're using, because some of the models will generate numbers that fit really well but don't actually make sense. And so the things that you need to consider are whether the system's in equilibrium or not, whether it takes more time to reach equilibrium and so your adsorption process is in the kinetic stage, or whether or not it's possible for multivalent binding to happen. And depending on which system your experimental system fits, then you can actually generate a curve that predicts energies and actually helps you model the system much better.
Thank you very much.
Thank you.
Thank you.
Thank you, guys.